sklearnsvmOneClassSVM. Description: OneClassSVM is an unsupervised machine learning algorithm used for anomaly detection. It learns a boundary around the normal data points and classifies any data points outside this boundary as anomalies. Inputs: X a 2D array containing the training data. Each row represents a data point. Kernel: the kernel function used for the SVM. Common options include RBF, linear, poly, and sigmoid. Outputs: model: the trained one-class SVM model. YPREDA1D array containing the predicted labels for new data points. 1 indicates an anomaly. -1 indicates a normal point. Steps: training: the algorithm learns a boundary in the feature space that encloses the normal data points. Prediction: for new data points, the algorithm calculates the distance to the learned boundary. Data points outside the boundary are classified as anomalies. Metrics: accuracy: the percentage of correctly classified points normal and anomalous. Precision: the proportion of correctly identified anomalies out of all points classified as anomalies. Recall: the proportion of correctly identified anomalies out of all actual anomalies. F1 score: the harmonic mean of precision and recall. Visualization plots: decision boundary visualizes the learned boundary in the feature space, separating normal data points from anomalous ones. Scatter plot shows the distribution of data points in the feature space, with anomalies highlighted. Fine-tune parameters. Kernel: the type of kernel function used. Experiment with different kernels to find the best fit for your data. Nu: the fraction of training data points expected to be anomalies. Higher values lead to a more relaxed boundary. Gamma: the kernel coefficient. Higher values indicate more complex decision boundaries. Uncertainty methods. Confidence score: the distance of a data point from the learned boundary can be used as a measure of confidence in its classification. Higher scores indicate higher confidence. Challenges and fixes. Challenge 1: choosing the optimal kernel and parameters for the specific dataset. Sample use case: using a linear kernel for highly nonlinear data can lead to poor performance. Fixes: experiment with different kernel functions and parameter settings to find the best combination for the dataset. Use cross-validation to assess performance on unseen data. Challenge 2: handling imbalanced datasets where the number of anomalies is significantly less than the number of normal data points. Sample use case: anomaly detection in network traffic where the majority of data points are normal and anomalies are rare events. Fixes: use techniques like oversampling or undersampling to balance the dataset. Consider using outlier detection algorithms designed specifically for imbalanced data.